Okay, next we want to look at the definition of graph of a function. Graph of a function. So what is the definition of graph of a function? So let f, let's say from A to B, be a function. Then the graph of f denoted by, let's say, GF is defined as the set of all pairs of the form A and B, such that B is equal to f of A, and A comes from the domain. So set of all pairs where the first coordinate comes from the domain. Second coordinate is f of first coordinate. In other words, the first coordinate is an input and the second coordinate is an output corresponding to the given input. The set of all such pairs is called the graph of a function. Okay, so normally we sketch the graph of a function using x-axis and y-axis. So x-axis, we use inputs or locate inputs on x-axis and the outputs on the y-axis. So let's say if you have a graph of f, let's say this is, let's say y equals f of x. And let's say we have a point, let's say A and B here. So then A and B lies on the graph of f if and only if B is equal to f of A. For example, let's say if I say f from R to R, f of x equals 2x, is let's say 1 and 3 a point on the graph of f. So how do we know that a point is on the graph or no? If the first coordinate comes from the domain, well, here the domain is all real numbers, so the first coordinate is 1, which belongs to the domain. Well, that's okay. And then the second coordinate should be f of the first coordinate, so the output corresponding to input. Now, if the input is 1, the output will be f of 1, which is 2, not 3, right? So 1 and 3 will not be on the graph of f. So the answer is no, since f of 1 is equal to 2 is not equal to 3. So that means 1 and 3 does not lie on the graph of f. Okay, another example. Let's say f from n to n. Let's say f of x equals x squared. Sketch the graph of f. So what is graph of f in this case? So graph of f equals the set of all pairs where the first coordinate comes from the domain n. Now, what is the first element of n? 0, and then the output should be f of 0, which is 0 squared, and that's 0, right? All the pairs, that graph is all the pairs where the first coordinate comes from the domain. Second coordinate is f of the first coordinate. Now the first element in the domain n is 0. So I start with 0, comma, the second coordinate is f of 0, which is 0. Next element is 1. Second coordinate has to be f of 1, which is 1 squared, and that's also 1. Next element is 2. F of 2 is 4, 2 squared, which is 4. And then 3 and 9, and so on. So this is the graph of f. The graph of f is set of all these pairs. Now, if you want to sketch them on xy axis, so this is x-axis, y-axis, I just need to locate these points because that's what the graph of f is by definition. And therefore, if I want to sketch it, I just need to locate these points. 0 and 0 is here. 1 and 1 is here. And then 2 and 4 is here. 3 and 9 is here, and so on. So that's it. So graph of f, some students get confused here because they think graph has to be always a curve. The graph does not have to be a curve. Yeah, in many problems in, let's say, calculus or pre-calculus, the graph was a curve because the domain that you considered for your function was real numbers or an interval, let's say. In those cases, the graph became a curve. But here, for example, if the domain is just some discrete set, for example, natural numbers, then the graph is just some points and not a curve anymore. Okay. Now, the next thing we want to look at is one-to-one and onto functions. One-to-one and onto functions. So when do we say that a function is one-to-one? One-to-one functions. So let f from A to B be a function. We say that f is one-to-one if f has no repeated output. Mathematically, f is one-to-one if f of, let's say, A equals f of B implies that A is equal to B for every A and B in domain of f. Okay, so let me explain this. Remember, for functions, we said that if we have to assign exactly one output to each input. But we did not say that we are not allowed to assign same output to two different inputs. So potentially it's possible that we have same output for two different inputs. For example, in the example of the height of the students. So it is potentially possible that two different students, let's say student number 1 and student number 10, let's say both of them are 160 centimeters. Potentially that's possible, right? So student number 1 and student number 10 are both 160 centimeters. I still have a function because I'm assigning exactly one height to every student. So I still have a function, but I have a repeated output, meaning that 160 centimeter as an output occurs twice, one time as the height of student number 1, one time as the height of student number 10. And therefore I have a function, but I do not have a one-to-one function. If you want to have a one-to-one function, you should not have a repeated output. Once you find a repeated output, then the function is not one-to-one anymore, okay? So f is one-to-one if f has no repeated output. Mathematically, why do we say this is the equivalent mathematical definition for one-to-one function? F of a equals f of b must imply that a is equal to b. Why? Because f of a equals f of b means two outputs are equal. Remember, f of x is the output, right? So f of a and f of b are equal means two of the outputs are equal. If you want to have a one-to-one function, under which circumstances you're allowed to have two equal outputs? Only if their corresponding inputs are also equal, right? Because if the inputs are not equal, but the outputs are equal, well, that means you have a repeated output. Like student number 1 and student number 10, there are different people, different inputs, but their outputs are equal. Both are 160 centimeters. And then I will not have a one-to-one function. But if you want to have a one-to-one function, means whenever two outputs are equal, then the inputs must be also equal, because otherwise you would have a repeated output and you won't have one-to-one function anymore. So this is a mathematical definition of a one-to-one function. So for example, let's say f from R to R, and then f of x equals x squared. This is not one-to-one. Why is it not one-to-one? How can I show it's not one-to-one? If I can find two different inputs with the same output, well, then that means I have a repeated output and therefore I will not have a one-to-one function. Which two different inputs here have the same output? For example, to take, let's say a equals 1, b equals -1, then f of 1 equals f of -1 equals 1, right? So that means we have two different inputs with the same output. And that means f is not one-to-one. Two different inputs, same outputs, f is not one-to-one. Another example, let's say f from R to R. F of x equals 3x minus 1. Show that f is one-to-one. Okay. Okay, do you think if I say, for example, let's say take a equals 2, b equals 5, then f of 2 will be 5, f of 5 will be 14. So I will have two different outputs and two different inputs. And then I can say f is one-to-one. Different outputs. And then f is one-to-one. Do you think this is a correct approach? I took two different inputs and they have different outputs. And then I conclude f is one-to-one. This is wrong. Why is it wrong? Because we know that we learned, in this course and also previous courses, that in mathematics, if you want to show something is correct, or if you want to prove something, your proof has to be in general, not with examples, right? If you want to show prove something, it has to be in general, not with examples. But if you want to show something is false, then you can give one example, which is called counterexample. The previous one, we wanted to show that the function is not one-to-one. So we gave one example of two numbers, two inputs with the same output. But here we want to show that the function is one-to-one. So the proof has to be in general, not with examples. How can we give the proof in general? We have to use the formal or mathematical definition. F of A equals F of B must imply A is equal to B for every A and B in the domain, right? So correct solution. Let F of A equals F of B for A and B in domain of F, which is all real numbers here. Then what can we say? Then F of A, how much is F of A? F of X is 3X minus 1. So F of A is 3A minus 1 equals F of B, which is 3B minus 1. And then that means 3A must be equal to 3B. And that means A must be equal to B. Okay. Then we want to look at the concept of increasing, decreasing functions. Increasing, so next. We still have to do onto, but before doing onto, because increasing, decreasing is also related to one-to-one functions. So let's do this first. Increasing, decreasing functions. So definition, we say that F, let's say from A to B, is increasing if F of A is less than equal to F of B for every A and B in domain which is A with A less than B. So increasing function means whenever you consider A and B with A less than B, so if you have two inputs, the first input less than second input, then the first output has to be less than equal to the second output. Also, or similarly, the F from A to B is called decreasing. When can we say decreasing? If F of A is bigger than equal to F of B for every A and B in A with A less than B. So decreasing means as you increase the inputs, the outputs must decrease. See, in the increasing, as you increase the input from A to B, the output also increases from F of A to F of B. But here, as you increase the input from A to B, the output decreases from F of A to F of B. So also, F from A to B is called strictly increasing. Strictly increasing if F of A is less than this time F of B for every A and B in DF with A less than B. And similarly, f from A to B is called strictly decreasing if f of A is bigger than f of B for every A and B in DF with A less than B. So strictly increasing is similar to increasing, but increasing we have f of A less than equal to f of B. This time we have f of A less than f of B. So the inequality must be strict in order to have strictly increasing, and similar definition for strictly decreasing. So let's look at an example. Let f from R to R and f of x, let's say, equal to minus 3x plus 1. Show that f is strictly decreasing. How can I show that f is strictly decreasing? So first we have to think about it. Should we prove it with examples or with general proof? Here we want to show something holds, something is true. So our proof has to be in general. How can I do proof in general? So I can start with some A and B. So let A and B in R with A less than B, right? Strictly increasing, remember? A less than B. Then I need to show that f of A less than f of B. F of A is less than f of B. Then f of A is how much? Minus 3A plus 1. So it's strictly decreasing. I have to show that f of A is bigger than f of B. So minus 3A plus 1 is bigger than minus 3B plus 1, which is f of B. Why is that? Because, if A is less than B, which is my assumption, then if I multiply both sides with minus 3, so you know from pre-calculus, if you multiply an inequality with a negative number, inequality will flip. And then if you add with 1, then you get minus 3A plus 1 bigger than minus 3B plus 1, which is what I wrote above, right? So I just justified why minus 3A plus 1 is bigger than minus 3B plus 1. And that means f of A must be bigger than f of B, which means f is strictly decreasing. Strictly decreasing. So why did I say that this is related to one-to-one function? The next example says, show that each strictly increasing function is one-to-one and part B, show that each strictly decreasing function is one-to-one. So if you do one part, the other part is similar. So proof part A, we want to show that. So suppose we have a strictly increasing function and we want to show that it has to be one-to-one. So suppose that f from A to B is strictly increasing. Remember, always the proofs has to be in general, not with the example. Some students give an example of a function which is increasing and is one-to-one. Those students won't get any point if this was a question in the exam. Because the proof has to be in general. Has to be in general means what? Means use letters, right? So let's consider an arbitrary function, let's say f from A to B, which is strictly increasing. And we want to show that f is one-to-one. Want to show f is 1 to 1. How can I show that the function is 1 to 1? I have to start with f of a equals f of b, right? So let f of a equals f of b for which a and b, for a and b in domain of f. And what do I want to show? I want to show that a has to be equal to b. We want to show a equals b, right? This, because if f of a equals f of b implies a is equal to b, then that means the function is 1 to 1, which is exactly what I want to show. So in order to show that a is equal to b, let's use proof by contradiction. So proof by contradiction. In proof by contradiction, we assume what we want to show is wrong. So suppose that a is not equal to b. If a is not equal to b, if two numbers are not equal, then there are two possibilities. Either the first number is smaller than the second one, or first number is bigger than the second one. Then either a less than b or b is less than a. Now, if a is less than b, then f of a is less than f of b. Why? A less than b implies f of a is less than f of b. Why? Because I was assuming that f is strictly increasing, right? Read the question. Show that each strictly increasing function is 1 to 1. So I'm taking a function f which is strictly increasing, and I want to show it's 1 to 1. So my assumption is that f is strictly increasing. Therefore, if a is less than b, I can conclude f of a is less than f of b. And this is contradiction. Let's say, since f is increasing, strictly increasing, and this is contradiction with f of a equals f of b. Remember, my assumption was f of a equals f of b, but here I said f of a, concluded f of a is less than f of b. That's a contradiction. Similarly, if b is less than a, then f of b will be less than f of a. And again, contradiction with f of a equals f of b. So thus we can conclude that a is equal to b, and that means f is 1 to 1. Okay, so another topic related to one-to-one functions is invertible functions. Invertible or inverse of a function, and also invertible functions. So I have to give you a recall about composition of two functions. Composition of two functions. So let's say let f from a to b, and g, let's say from b to c. Then g or f will be from a to c. and is defined as GOF of X is defined as G of F of X. Right, so if I want to show you what happens here, see, we have an input X in the first set, let's say A, like let's say small a. Then we apply F to it, we get F of A, which is some element in B. So the outputs of F are in the set B, but also the inputs of G are also chosen from the set B. So we apply, so this F of A, which was originally output of F, now is going to be, and now it's going to act as an input of G. And then we can apply G to it. And then we get G of F of A as the final output, which is some element in C. So this is like, remember, each function acts like a machine that has an input and an output. So we start with a machine F, we start with the original input A, we get an output F of A, then we connect this to the second machine. You can imagine, in the factories, there are different machines that they're connected to each other, right? So this is like that, we connect F with G. So we first apply F to get F of A as an output of F, and then we apply G as a second machine to get G of F of A. So for example, let's say F from R to R, F of X equals, let's say, 2x, G from R to R, G of X equals X over 2. Find FOG of X. FOG of X will be F of G of X. G of X is what is X over 2. So this is F of X over 2. And what is F of X over 2? F of X is 2x. So F of X over 2 will be 2 times X over 2, which is X. So FOG of X becomes X. That means, so this is called, if you remember from pre-calculus, this is called an identity function, right? So identity function denoted by, let's say, IA, let's say from A to A, is the function such that IA of X is equal to X for every X in A. So its identity function is a function whose output is same as the input. So it's basically acts nothing. So it does not transform X to anything. The input and output are the same. So it's like a machine that is turned off, whatever input you put inside, you get the same output. Okay. Now, when do we say that the function is invertible? So invertible functions so let F from A to B be a function. We say that F is invertible if there exists a function G from B to A such that f or g becomes identity function on B, and g of f becomes identity function on A. So when you compose f with its inverse, so g is called inverse of f. So under these circumstances, g is called the inverse of f and is denoted by f inverse. So if I want to show you what happens, see you have, let's say, A and B, and let's say you have A, and here you get f of A, so let's say small b. But now if you compose this with f inverse, you get the original input back. So invertible function means there is a function called g that when you connect it with f, composition was a connection of two machines, right? When you connect them together, at the end, they act like nothing. So you get you start with an input A, you apply f to it, you get f of A, which may not be same as A, but then after you apply the second machine called f inverse, then you get the original input back. So basically you perform something, but then you undo that transformation to get the original input back. So this is f, and this is f inverse. So the example, a simple example we can consider was this one, f of x is 2x, g of x is x over 2. So we start with an input x, we apply f to it, we get twice that number. For example, if we start with 5, then f of 5 will be 10. But then if we apply g to it, g divides by 2, which is basically undoing what f has done. So we start with 5, then we multiply with 2, we get 10. Then we apply g to it, 10 by 2 will be 5 again, right? So when we connect f with g together, if we start with x, we end up with x as well, which is what we have shown already here. F or g of x equals x. F multiplies by 2, g divides by 2. So when you connect them together, they do nothing. So let me call, for example, this example. Let's call it example 1. So here I can say example 1 above shows that f of x equals 2x is invertible and f inverse of x is equal to x over 2. F inverse is also from R to R. Right? That function g, because when we compose f with g, we get the identity function. So that means that function g is called f inverse. So G was x over 2, so f inverse of x is x over 2. Okay. So now which functions are invertible? Well, we can always compare this with the set of numbers. In numbers, which numbers are invertible. And we know that every number except 0 is invertible with respect to multiplication. And reciprocal of the number is your inverse. But in the set of functions, which functions are not invertible? But of course, if you have a function 0, constant function 0 still is not invertible. But there are so many more functions that are still not invertible. And you saw in pre-calculus that if a function is not one-to-one, then it will not be invertible. And if it is one-to-one, it will be invertible. So let me leave this as an exercise. Show that a function, let's say f from a to b, is invertible if and only if it is one-to-one. So this is an if and only if exercise. So you have to prove two things. One time you assume that your function is invertible and then show that it has to be one-to-one. And then the second problem, you assume that your function is one-to-one and show that it has to be invertible. So there are two things that you have to prove. Okay, next we want to look at the onto functions and also image of a set. So let's start with the image of a set. So let f from a to b be a function, and let S be a subset of A. The image of S under F, denoted by f of S, is defined as follows. So f of S is defined as the set of all elements of the form f of A, where A comes from S. So in particular, if S is equal to the whole domain, then f of S equals f of A equals a set of all elements f of A, where A comes from the domain. And that's exactly what the range is. See, so far we talked about f of a number. But here we are defining f of a set. F of a set S is defined to be the set of all elements of the form f of A, where A comes from that set. Now, if your set S is the whole domain, well, the set of all elements of the form f of A, where A comes from the domain, means the set of all outputs, right? And set of all outputs is range. So we are giving a definition more general than the range, f of any set. Now, if your set is the whole domain, you get the range. Otherwise, you get something which is a subset of the range, right? So let's look at an example. And let's say let f from is again n to n, f of x equals x squared. Find f of s, where s is equal to, let's say, 2, 5, 10. See, we want to find f of a set. Which set? The set containing 2 and 5 and 10, which is a subset of n. Remember this s, if you want to find f of s, your s has to be a subset of domain. And of course, here s is a subset of domain. So what is f of s according to the definition? F of s is equal to the set of all elements, f of a, where a comes from the set s. So it's going to be f of 2, comma f of 5, comma f of 10. What is it? F of x is x squared. So f of 2 is 4, f of 5 is 25, f of 10 is 100. That's it. So a set containing 4 and 25 and 10. That's my f of s in this example. Okay. Now, another concept which is very important and it's mentioned in exercises is inverse image. Inverse image of a set. So again, let f from a to b be a function. And assume and let S this time be a subset of B. The inverse image of S under F, denoted by F inverse of S, is defined as follows. F inverse of S is defined as the set of all elements A inside the domain such that f of A belongs to S. Let me explain what this inverse image is. Let's say you have A and B, domain and codomain, and F acts between A and B. Now, if I start with some subset of B, see, for inverse image, we start with the S, which is subset of B. So let's say that I have an S here. So what is F inverse of S? It's going to be all elements inside A for which they are going to be mapped inside S. So let's say, for example, these elements are going to be mapped to S. So for example, this is going to be mapped here, this is going to be mapped here, this is going to be mapped here. So then this is going to be F inverse of S. And let's assume, anything outside of this S is going to be mapped outside of S. So if I want to find F inverse of a set, I have to look at the domain and look at which inputs are going to be mapped inside S. The set of all such elements going to be called F inverse of a set. So please note here, we are defining F inverse of a set here. If you want to define an F inverse of a number, well, then you need to find F inverse of F first. See, we already defined inverse function, right? So when you want to find F inverse of a number, first of all, your function has to be 1-to-1 so that it becomes invertible. And then you find inverse of the function. And once you have inverse of the function, you can find f inverse of a number. But here we are defining f inverse of a set. F inverse of a set, you have to use this definition. And to define f inverse of a set, your function does not have to be one-to-one. And therefore does not have to be invertible. This is just a notation, okay? So it happens to be same notation as the one you use for inverse of a function. And that's why it's a little bit confusing. In my experience, many students get confused because this notation and the notation for inverse of a function are the same, but this is f inverse of a set. For that one, we use f inverse of a number. So let me mention here that as an important remark, f inverse of S can be defined even if the function is not invertible, i.e. if f is not one-to-one. So let's look at an example. Let's say f from R to R, f of x equals x squared. Find f inverse of, let's say, 4 and 9. F inverse of a set, 4 and 9. How can I find it? So f inverse of 4 and 9, according to my definition, is the set of all elements inside domain such that f of a belongs to my set 4 and 9. I have f inverse of a set. How can I find it? I have to look at my inputs. I have so many inputs. Every real number is an input here. And then I have to see which inputs are going to be mapped to an element inside my set 4 and 9. So the set of all elements A in R such that f of A is inside 4 and 9, meaning that A, which is the input, must be mapped to an element inside 4 and 9. So think about it. F of x is x squared. Which elements in the domain is going to be mapped to an element inside 4 and 9? Let's think about the elements in the domain. For example, 0 is one of the inputs. Is 0 going to be mapped to something inside 4 and 9? No, because 0 squared is 0, not 4 or 9. 1 is another number. F of 1 is 1, not inside 4 and 9. What about 2? 2 will be mapped to 4, which is inside 4 and 9. So 2 is one of the elements inside this set. So how can I find all of them? So if I simplify this set, A belongs to R such that f of A is A squared. A squared belongs to 4 and 9. So A squared belongs to 4 and 9 means what? Means A squared is equal to 4 or A squared equals 9. Because 4 and 9, it has only 2 elements, 4 and 9. So A squared belongs to 4 and 9. So what does that mean? That means either A squared has to be equal to 4 or it has to be equal to 9. And then this means, well, A squared equals 4 means A is equal to 2 or A equals minus 2. And A squared equals 9 means A is equal to 3 or A equals minus 3. So this is simply 2 minus 2, 3 minus 3. So we show that f inverse of 4 and 9 is equal to 2 minus 2, 3 minus 3. So again, I repeat one more time. F inverse of a set is also a set. Is in fact a subset of domain. F inverse of a set is a subset of domain. Which subset of domain? A subset of domain containing all elements which are going to be mapped to something inside your set, which is in this case 4 and 9. Well, 2 is mapped to 4, minus 2 is also mapped to 4, 3 mapped to 9, and minus 3 mapped to 9. So these 4 elements will be F inverse of 4 and 9. So let's say this is part A. Now let's do part B. Find F inverse of, let's say, 2. F inverse of 2 means the set of all elements A such that A squared belongs to 2. A squared belongs to 2 means it's 2 itself. And which square of which elements are 2? Root 2 and minus root 2. C, find, let's say, F inverse of minus 2. And this one by definition is the set of all elements A in R such that A squared is equal to minus 2. A squared equals minus 2, but there is no element A in R with A squared equals minus 2. So this is empty set. So F inverse of minus 2 is an empty set. And that's okay. You know, we said that F inverse of a set is a subset of domain, but empty set is also one of the subsets of the domain. So it's okay for answer to be empty set. And part D, find, let's say, F inverse of 2 itself. See, in part B, we found F inverse of the set containing 2. But here you want to find F inverse of 2. There is no set notation anymore. What do you think this one is? So that's why I say it's a little bit confusing. We have same notation for F inverse of a number and F inverse of a set, but different concepts. F inverse of a set, I just said, you have to, it's a subset of domain. You have to see which elements of domain are going to be mapped to inside that set. But F inverse of a number, first you have to find inverse of the your function. And if you want to find inverse of your function, first your function has to be invertible. And when can I say my function is invertible? If it's 1-to-1. But this function is not 1-to-1. Right? This function is not 1-to-1. Therefore, it's not invertible. Therefore, F inverse does not exist. And therefore, F inverse of number 2 is undefined. F inverse of 2 is undefined since F is not 1-to-1. That means F is not invertible. That means F inverse of 2 is undefined. Okay, now let's look at onto functions. Definition. We say that F from A to B is onto or a surjection if range of f, which we denoted also with f of a, is equal to b, i.e. The codomain and range must be equal. Remember that we said, in general, codomain might be bigger than the range, might be equal to range, might be bigger than the range. Now, if they're equal to each other, then we call the function onto or surjective. So, and the next definition, we say that f from A to B is a bijection if f is 1-to-1 and onto. So let's look at some examples. Let's say f from n to n, f of x equals x squared. Is f onto? So onto means, can I say that the range is equal to the whole codomain? Codomain is all natural numbers. Is the range same as all natural numbers? Range instead of all outputs. What are the outputs here? 0 squared, which is 0, then 1 squared, which is 1, 2 squared, which is 4, 3 squared, which is 9. So 0, 1, 4, 9. So these are the outputs. Is it same as the whole codomain, which is all natural numbers? The answer is no. So we know that if in mathematics, if you want to show something is not right, we just need to give one counterexample. So let's give one counterexample. So the answer is no. Take, let's say some b, let's say b equals 2. Then b will not be, which is in the codomain. Then b equals 2 will not be in the range of f. Otherwise, 2 belongs to range of f, then 2 will be equal to x squared. And that means x equals plus minus root 2, but neither root 2 or minus root 2 belong to n. So that means range of f is not equal to n, the codomain. So please remember that the codomain always contains the range. Now, if you want to show that your function is not onto, you have to find one element of codomain, at least one element of codomain, which is not in the range. So here, for example, 2 is in codomain, not in range. Why? Because if it was in the range, then 2 has to be equal to x squared. Range means the outputs, right? So output means f of x, which is x squared. So 2 equals x squared would imply x is either root 2 or minus root 2, but neither of these numbers belong to the domain. Remember, x must come from the domain, right? But root 2 or minus root 2 are not in the domain, which is the natural numbers in this case. Therefore, that means range of f and the codomain are not equal, and therefore the function is not onto. This is another example. Show that, let's say f from R to R, f of x equals x cubed plus 1 is a bijection. So do you remember what bijection means? Bijection means one-to-one and onto. So if you want to show that the function is bijection, you have to do two things. You have to show it's one-to-one and you have to show it's onto. So first, showing f is one-to-one. Okay, I want to show f is one-to-one. I want to show some statement is true, so I cannot use examples. I have to do the proof in general. In general means what? Means I have to start with f of a equals f of b. So let f of a equals f of b for which a and b, for a and b coming from the domain, which is all real numbers. Then, what can I say? F of a is a cube plus 1, f of b is b cube plus 1. And then that means a cube is equal to b cube. And if I take cube root, I'll get a equals b. So f is one-to-one, and now let's show that f is onto. Next, showing that f is onto. To do this, we need to show that range of f is equal to the codomain, which is all real numbers. Onto means range of f must be equal to codomain, which is all real numbers. So how can I show this? Again, you want to show two sets are equal. Of course, one direction is always valid, right? So RF is a subset of R. So remember that, please remember that RF is always a subset of codomain. So this direction always holds. This is not what the direction that determines whether the function is onto or not. Range is always a subset of codomain for every function in the world. The other way may or may not hold. The codomain may or may not be a subset of range. So that's what determines whether the function is really onto or not. I need to show this, so this part is okay. Also, R, also we will show that R is a subset of RF. This is what, like I said, whether codomain is also a subset of range. If yes, the function is onto. If no, the function is not onto. So how can I show that the range R is a subset of RF here? So taking elements, right? Next we'll show this. So take, let's say Y, or let's say T, doesn't matter, you can call it Y or T. Let's say T belongs to R. And I want to show that belongs to range. How can I show that it belongs to range? If I can show that T is equal to f of some input, then that means it has to be in the range. So T equals f of x. That gives T equals x cubed plus 1. F of x equals x cubed plus 1. Here. So that means T minus 1 is equal to x cubed. And that means x is equal to cube root T minus 1. Thus, t is equal to f of x. For which x? For x equals cube root t minus 1. So that means t belongs to the range. And remember, cube root t minus 1. Please always be careful to check with the x that you get this way. So remember, so I took some t in the codomain, which in this case is all real numbers. I have to show that t, if I want to show that the function is on 2, I have to show that this t belongs to the range. How can I show that it belongs to range? I have to show that it's equal to f of some x for some x in the domain. So I put t equals f of x. I found the value for x. Then you have to check that this x is inside the domain or no. Because if x is outside the domain, then that's not acceptable. But this x is cube root t minus 1. And cube root of a number is, of course, always a real number. And my domain in this case is all real numbers. See? And from R to R. So cube root t minus 1 is a real number. So it's an element of domain. So I showed that t is f of some input chosen from the domain. That means t is an output. Therefore, t belongs to the range. So I took some t in codomain. I showed that is in the range. So that means f is on 2. So we show that this f is 1 to 1 and on 2. Therefore, it's a bijection. All right, guys. So for the upcoming test 1, it will cover from the beginning until end of 2.3.4. So test 1. I will cover until end of 2.3.4, which means at 2.3.5 and 2.3.6 will not be covered in this test. Okay, guys, so please let me know if you have any questions. You can send me an email or feel free to attend the office hours. If you have any questions about any topics or any general questions. Okay, thank you guys and see you next time.